Okay, we are recording, but I really don't want to share that screen, but that's what you're going to get now until I can find my PowerPoint. And Andy's here. Welcome, Andy. Howdy. I've got to do something else to, here we go. All right, and we'll go from current slide. It's taking a while, but it's getting there, I think. Well, maybe not. There we go. Now, as soon as I get all this stuff loaded, I can only see a couple of people at a time. Actually, I can't see you, I can just see your names. So what I'm going to do is move you up to the corner. You got to sit in the corner because you're bad. Okay. So right now I have JJ, Jonah, Joanne, all three starting with J's. Andy, you're the busted flush here. You're the outlier. You don't start with J. All right. Is anyone else in the room besides the four of you? Can you see any other names?
That's all I see.
Say again?
That's all I see.
Okay. All right. As soon as you see someone come up, I may or may not see them, so let me know if you see someone else join, because that's how we have to do. Okay. Now, any news since last time we met? I think there's one bit, and if you remember, technically I have office hours from 8 to 10 on Monday and Wednesday mornings. That's still happening. And it was listed that I had office hours from 4 to 6 on Monday evening. Well, those have just been preempted by advising hours, okay? Well, not totally. I am open as an advisor from 4 to 7 on Monday evening, and then again from 8 to 12 on Friday mornings. So if any of you need advising or need to talk with me as an advisor, you need to sign up through that new thing they have, the Virtual Advising Center. You'll have to go to your quick links to see how to get there. I think it comes right up somewhere there. I've never done it from the student side, so I don't know exactly. So that's how we're doing advising now. We're trying to do everything that we did before on campus in the virtual campus. So if you can't get me on a Monday evening or a Friday morning when I'm supposed to have office hours, I may be advising. But my whole schedule isn't usually filled. Most of it may be. I can't remember now how many I have. I know I have at least 3 this evening, and I know I have some on Friday, but I don't know how many. They're in half-hour blocks, and I believe mine start at 4:30. I have one at 4, one at 5:30, and one at 6. I may have others. I've got to go out there and finish checking. I was trying to do that before this class started. So, sorry if I'm losing office hours, but the dean thought that we department chairs didn't have enough to do, so we're having to advise 2 days a week for so many hours a day. So, and those are the only times I can do it is when I have office hours. All right, how about y'all? Do y'all have experienced any issues, problems, things that we need to address? Okay. I'm pretty sure. Yes, what was that?
So, who are we supposed to talk to if one of your teachers is not doing any Zooms and barely, getting in touch with the students?
Okay. I think I understood. Was that Andy talking?
Yes, sir.
Okay, because your name isn't popping up, but I thought it was your voice. My understanding of your question, what do you do if one of your teachers, instructors, is not putting anything out there? Is that right?
Yeah, because the only thing he put out was an exam, but I don't know what I was supposed to be looking at or whatever to do this exam.
Okay. Do you feel comfortable in front of the whole group telling me who the instructor was?
Well, I can't. I think it was Dr. Brown.
Dr. who?
Dr. Brown, the one who does physics.
Does physics?
Yeah.
That's Bryant, right?
Yeah, Dr. Bryant. Yes,
Bryant, okay. And what has he done? He just put out something on Blackboard and that's all?
All he did was post an exam 3, and I never knew there was an exam 3 nor an exam 2. So,
Okay. All right.
he also hasn't done live videos like you have or any of that. So.
Okay. What you need to do is can you email Dr. Bryant? Do you have his email address?
Yes, sir.
Okay. Have you done that yet?
Not yet, because I've been busy at work. So.
Okay. What you need to do, I need to get in touch with him today too, so it's good that you told me this because I was going to try to give him a call today. I don't know when, but sometime I need to give him a call because there was another issue that came up. So what I'm doing, I'm waiting on the dean. I don't have his number here at home, and the dean said she would have someone send me his number. I haven't found that yet, so that if I had gotten it, I would have already called them. So I'm going to try to contact someone also to get a phone number from him if she forgot to do that. So I'll be in touch with him, but you get in touch with him too, and express your concerns. Let him know what's going on because he's done a lot of online courses before, and he's maybe treating this more as an online course than a virtual course. So I did see an email from him when I was looking for my advising stuff today, and I didn't have a chance to answer it because I only had like 7 minutes to go before this class started. So I'll also be trying to email him today too. But the trouble is, all my office hours are gone now because I'll be advising. So it'll probably be much later this evening before I'll be able to get in touch with them. And so you can probably get in touch with them sooner than that. So please do that, and I will be in touch with them hopefully this evening. It depends on how late my advising goes, but I will have to get in touch with them this evening too. But thanks for telling me, and try to get in touch with them and find out what's going on, and you can let them know I'm going to be trying to email him as well because I saw that he sent me an email and also had something that the dean had asked me to share with him. So thanks. Sorry about that it's happening, but try to get in touch with him. I think he's pretty good about clearing it up. All right. And by the way, I know he doesn't have a laptop, so he may be using a home computer. He may be using his telephone. I don't know what he's using. That kind of stuff I have to find out from him. Okay? All right. Any other issues? Has anyone else joined the class since I called or acknowledged the role of JJ, Jonah, Joanne, and Andy? Anyone else here?
That's it.
You don't see anybody else? Okay. All right. If there's no other issues or questions, I was going to say, I don't think it was this class, but I can't remember which one. I'm only teaching 8 classes now, so I can't keep up with who said what. In one of my classes, one of the students could not access the messages. That wasn't anyone in this class, was it? I'm guessing not because all of you are here, okay? But I don't remember that it was anyone that was here last week. Do you recall?
Recall anybody saying anything about that?
Okay. I think it was my first class on Tuesday, Thursday, not the first class this morning. So I think we're okay. All right. Any other issues before we get going on the calculus? Okay. My memory and my mark in the book was we're in chapter 4, and right now I can't see the title of it, but it's Applications of Differentiation. And we're just say again?
Houston's coming in.
Who is?
Houston.
Houston, excellent. Okay. All right, let me find them here. I know there he is. All right, got Houston here. And I guess while we're on this subject, has anyone got any way to get in touch with Christian Graham? He wasn't there that last Monday before we shut down, so he did. I don't know how much word he got about it, but I haven't seen him since. Did anyone share any contact information with him? I hope he's able to watch the YouTube videos, but I don't know. Let's see, who else? I don't believe Devontae has logged in since we got started. Has anyone got any way to get in touch with Devontae?
I just sent him a text just now.
Okay, great. Thank you.
I just told him that he's going to get on Zoom because he's got to leave class now.
Okay. Yeah. So, did you basically coach him on how to log in and stuff? Okay. I can't hear a response. Okay, I still haven't heard from Houston. I guess you've logged in and got audio? Maybe not. Well, hopefully you can hear us. So we're starting today. My memory was we finished 4.3 last time, and today we're starting 4.4, which is concavity and the second derivative test. Now, if you remember before, I think it was 4.3, we were talking about increasing and decreasing functions and the first derivative test to help you know what was going on with that. Now we're going to bring up a new concept, and that is one of concavity. Now this comes from the word concave, and I remember when we were doing lenses in physics, whoever the instructor was at that time, or teacher I had in school, let me get my pen set up, she said this: think of this as being concave, like the opening of a cave, and this is convex. Wait, I said it backwards. Well, depends on which way. If you're looking from this end, that's concave. If you're looking from that end, it's convex. We're not dealing with that kind of concavity quite. What we're dealing with is curving, that part of concavity. So we're not interested at all in whether something's convex or not. We're just interested in the concavity, or which way it's curving. Now that's probably a pretty lousy definition of it, but let's see what the book has. Our objectives here are to determine the intervals on which a function is concave up and concave down. I hope you have sort of a mental image of this. This would be something that's concave up. This would be something that's concave down. Okay? And it can take on any kind of form there. So we'll be determining intervals on which concave up or concave down. Now, if that same function changes from concave up to concave down, or from concave down to concave up, that is called a point of inflection. So we'll find those points of inflections on the graph of a function. And then we'll apply the second derivative test to find extrema of a function. Now we already know that how to do that using first derivative test. I think you'll find the second derivative test much easier. Okay? We'll see. Any questions so far? Any questions? Okay, I couldn't hear any. I thought I heard something in the background. I realize from other classes that sometimes y'all turn off microphones to cut down background noise. And so be sure, if you have a question for me, turn on your microphone, or I may not hear it. It may sense you, I don't know, but if you're trying to say something and your microphone's muted, I won't hear it. So But I can see one of the students in front of me right now whose microphone is muted, and he lives in the same household of another student I have, in fact, two other students that I have, and they said, yeah, they had to mute their phones because of all the background noise. So I can't remember what was going on in the house, but I understand that. Sometimes I have to too, so we have a dog barking downstairs, but I don't think that's bothering you here. So, concavity. What does that mean? You have seen that locating the intervals on which a function increases or decreases helps to describe the graph. It certainly does. That is a very clear description of the graph. In this section, you'll see how locating the intervals on which the first derivative increases or decreases, and how this can be used to determine whether the graph is curving upward or curving downward. So here's your definition of concavity. Let f be differentiable on this open interval I. Okay? Differentiable, what does that mean? Two features to be differentiable. Anyone remember what they are? One is like jazz. I don't know if you like jazz or not, but it's smooth. Okay? Or people consider it smooth. The second one is what?
Approaching the same limit.
Okay, and that almost defines continuous. Okay? Those are the two words, smooth and continuous. When you see the term differentiable, think this function is both smooth, that means it has no cusp, no corners, no angles. It's smooth. Every one of its turns is nice and smooth. It's also continuous. That means there's no gaps, no holes, no missing values. And that's what JJ, I think, was just meaning by the limits exist everywhere. Okay. And not only do they exist, but they are the same as the functional values. Okay. So, the graph of f is then concave upward on I, on that interval I, if or when f prime is increasing on that interval. So here, I just drew a little graph here, okay? Here, the first derivative is negative, isn't it? But here, just a little bit further down the road, it's still negative, but it's less negative. So that means the first derivative is increasing. Down here, that first derivative is what? Zero. That is an increase from a negative number. This is a very negative slope here, not quite as negative here, 0 here, and then what's it doing over here? It's positive, and more positive, and more positive. So that means that the first derivative is increasing on that interval, and that defines the function as being concave upward. But it's concave downward if the f prime, the first derivative, is decreasing. Well, here's the first derivative is what sign? What sign?
Positive.
Positive. Is it fairly large positive or small positive?
Worked out large.
Yeah, pretty large. How about here? Is it positive or negative?
Smaller positive.
It's still positive. Is it bigger or smaller than it was before? Smaller. Okay, so the first derivative is decreasing along there. There, at that last one I drew, what's the first derivative approximately anyway? 0. So the first derivative is going from very steep, not quite as steep, not quite as steep, to 0, and then what's it doing over here? What's the sign of it here, first derivative? Going downhill. It's negative, and then more negative and more negative. That means it's concave downward. It's concave downward on that interval I when f is decreasing, f prime is decreasing on the interval. Not f. F is a different issue. F is decreasing here, increasing there. but the first derivative is increasing all along there. F is increasing here, or reached its peak, extreme here, maximum here, decreasing here, but the first derivative is decreasing everywhere there. So it's easy to get these two confused, what F is doing as opposed to first derivative F prime is doing. Okay? So the following graphical interpretation is perhaps a little bit better looking than mine. Might be useful. If let F be differentiable on the open interval I, and there is expressing the open interval I. If the graph of F is concave upward on I, then the graph of F lies above all the tangent lines. Now, did we do this last week? Anybody?
I think we temporarily mentioned it.
Okay. That's the thing. See, in my Cal 3 class, we're doing concavity in multidimensional things. So I'm talking about concavity in both classes, and I can't remember. So I guess in the first derivative, they also talked about this. I'm getting the two classes crossed up. Have y'all seen this part before? Am I repeating anything we did last week? I have a feeling we are, but it may be because I did it in my other class. Did we do it in this one? Is this fairly new?
Yes, sir.
Okay. All right. We'll go on with it. So if F is differentiable on the open interval, the graph of F is concave upward, then the graph of F lies above the tangent lines on I. Now, I thought we did this before, but we didn't. Okay. And you see all the tangent lines are beneath the graph of the function. All the first derivative tangent lines. Okay? That's another way of looking at concave up. Okay? That's one I don't usually use that much, but it certainly works. If that helps you, use it. It's concave down. If F is differentiable open interval, the graph of F is concave downward, then the graph of F lies below the tangent lines. All the tangent lines are above the graph, not below the graph. So this is concave down. If the graph is below the tangent lines, it's concave down. It's just another way of looking at it. I look at it as it first was stated, is the first derivative increasing or decreasing. But that's sometimes, well, both of them have some issues, positives and negatives. But that's concave down. The first derivative is decreasing everywhere on that graph. Does that make sense? Okay. To find the open intervals on which the graph of a function is concave up or concave down, you need to find the intervals on which the first derivative is increasing or decreasing. Now, how did we tell when a function was increasing or decreasing? What did we do? What was your Jesus answer? Take a derivative. So guess what we're going to do when we're trying to determine if the first derivative is increasing or decreasing? Take the second derivative. Excellent. Okay. So, for instance, if this graph, the one that they have up here, f of x equal 1/3 x cubed minus x, that's your graph. That's it right here. Okay. They say, and just looking at this, what would you say, where would you say that looks like it's concave down? Doesn't it look like it's cupping downward from negative infinity up to somewhere around 0? There, I can't tell what it's doing, okay? But then from past 0, what's it doing? Concave up, okay? Now that's looking at the graph, and this one, it really does look like it may be 0 where that's happening. You can't trust your eyes though, okay? I believe it will be that, but we'll see, okay? Now, if you take your first derivative of that function, what do you get? Don't look down here. F prime of x is equal to, you're looking, aren't you? Say again?
X squared minus 1.
X squared minus 1. Perfect. Okay. Now, is there any place where that is increasing? In other words, the first derivative. Where is that first derivative positive?
X is greater than 1.
Yes, for x greater than 1, or actually less than minus 1, right? Two places where that first derivative is positive, okay? But that doesn't, well, that's not what we're looking for. That tells you, well, that the function is increasing less than minus 1 and increasing again past positive 1, and that it's decreasing in here. But that says nothing about the concavity. What we're interested there is, where is the first derivative increasing? Okay? And there the best idea, well, if you look at this, the first derivative is, how you tell whether it's increasing. If it's positive here, you know it's got to be increased. Well, I'm sorry. It's decreasing here. The first derivative is decreasing. That means the graph of the first derivative is negative. The slope of the first derivative is negative, going downhill. Okay? And the first derivative, the slope of the first derivative is positive. See what they've done here, and to me this is not all that instructive of a graph, because this almost makes it more confusing. But if you look here, the first derivative, like you said before, is positive here and here, and sure enough, the first derivative is above the x-axis at those two places. It's negative in between those two places, but that still doesn't tell you what it's, whether it's, well, yeah, it does tell you whether it's increasing or decreasing, because where the first derivative is negative, the derivative of the, for the first derivative to be negative, okay, not negative, the slope of the first derivative is negative. That's what gets confusing here. The slope of the first derivative is negative everywhere up to 0, and the slope of the first derivative is, okay, is increasing everywhere here. Well, it's increasing. Let me back off again. The slope of the first derivative is negative everywhere here and is positive everywhere here. So that means that the function is, if the slope of the first derivative is negative, that means it's decreasing. So therefore, this is concave downward here. The graph up here shows it much clearer than here. But if the slope of the first derivative is positive, that means it's up here, concave up here. Okay? So you just have to get in your mind what you're dealing with, which graph you're looking at. If you're not careful, it really will throw you. Okay? Here's where the magic happens. Similarly, the graph of, okay, going on with this. The graph of f is concave upward on the interval from 0 to positive infinity because f prime is increasing on that interval. Okay? The slope of the first derivative is positive. Slope of the first derivative. Okay. The following theorem shows how to use the second derivative of a function, just as JJ said, of a function f to determine the intervals on which the graph is concave up or concave down. So here's your test for concavity. Let f be a function whose second derivative exists. Now what does that tell you about the first derivative? If the second derivative exists, that means the first derivative has to be, what were those two words? The graph of the first derivative? Smooth and continuous. And sure enough, our first derivative graph was smooth and continuous, no cusps, no points, no angles, and no discontinuities there. Okay? Your first derivative, the second derivative, for it to exist, the first derivative's graph must be smooth and continuous on that open interval I. So, what we do, we look at f double prime, the second derivative. If that is positive, greater than 0, for all the x's on that interval, then the graph of f is concave upward. So much easier than trying to figure out whether the first derivative is increasing or decreasing. It's so much easier. Just take the second derivative. If it's positive, that means it's got to be increasing. If that second derivative is negative, that means the graph of f is concave downward, meaning the first derivative is negative. Not the graph is negative, but the first derivative is negative. So that then tells you whether you look at the second derivative and do it just like you did the first derivative to define the extremum. Now you use the second derivative to find concavity. Whereas the first derivative told you direction of the function, the second derivative tells you the shape of that function. Okay, concave up or concave down. So to apply that, locate the x values at which f double prime is 0, or where f double prime doesn't exist. Now, f double prime may not exist, but the well, this almost sounds, it says let f be a function whose second derivative does exist on the open interval, and yet over here they say, or it doesn't exist, because that also is going to tell you something. So use those x values to determine test intervals. Now, before we called those critical values. We've already used that term, so don't use it anymore. I mean, yeah, you use it with first derivative. But what we're going to do is you can think of those as indicating concavity. Okay? So where the first derivative or second derivative is 0 or the second derivative doesn't exist. Use those x values to determine the test intervals, and finally test the sign of f double prime, the second derivative, on each of those test intervals. Just like we did for first derivative, our test was where first derivative was 0 or doesn't exist, and then we did our test intervals. Now we do the same thing with second derivative. So this, I think, is example 1, though I can't see it. Yeah, this is it. Okay. Determine the open intervals on which the graph of f of x is equal to e to the minus x squared divided by 2 is concave up and concave down. So what would you do first? Same Jesus answer as before. Take a derivative. F prime of x. Okay, you answered that one right, but now I want you to take that derivative. What would that be? A little louder. Okay, it sounds like I hear someone trying to talk in the background, but I can't make out what you're saying. Or maybe I'm imagining someone's answering. What's the first derivative of that function? Get me started anyway. It's the derivative of e to the minus x squared over 2. Derivative of any exponential function is, I love exponentials because the derivative is itself, e to the minus x squared over 2. There's part of it right there. Derivative of an exponential function is that exponential function. That's the beauty of an exponential function. But in this one, what else do we have to do? What rule do we use? The what? I couldn't hear. I heard someone say some sort of rule.
I didn't understand the what rule question.
Yeah, that's what I'm asking. What rule do you use? I did the first part of this. I took the derivative of the e function. It is the e function. It's the same function. But this function, I need to use what rule to continue? This has an inner and an outer function. The outer function is e. I took the derivative of that one. Done. What do we still need to do? The integral of the inner function. This is the, somebody has to know this, don't you? An anchor has a, oh, you may not know, I was in the Navy. That may be a bad analogy. Every anchor has an anchor chain, okay? The chain rule. What does the chain rule tell you here? What's the derivative of this inner function here? Help me, somebody. Anybody? Derivative of minus x squared over 2. Or you could write that derivative of minus 1/2 x squared. So d by dx. What is that derivative?
Negative x.
Negative x. Perfect. Write that in front. You could write it on the back side of it, but then if you don't write neatly and don't get it dropped down low enough, you don't know if that's part of the exponential or not. It's not. It's out in front. Okay? There, you've taken the first derivative of that function. What is the next thing you've got to do? It's almost the same Jesus answer, isn't it? We're looking for concave up or down, concavity. What do you have to do to get concavity? Take the of the first derivative, which gives you the second derivative. Now, this is going to be harder to fit in here, because now what kind of rule do we use to begin with? Anybody? When you write two functions next to each other like that, what does that mean? What operation are you doing? Okay? I'm just looking for the operation now. Don't tell me what to do yet. What operation does it mean to have a minus x in front of a e to the minus x squared? What does this imply? I'll put a little dot there. Say again? I thought I heard someone say multiply. Please say that's what you said. Right? Isn't that multiplication? So guess what kind of rule we use? What's the product rule? Very good, okay? How does the product rule go? Anybody? Okay, I can't hear if anyone's talking. Okay, I hear a very faint something in the background. It may be hard breathing. I don't know what y'all are doing, but what's the first step in the product rule? You can do either one of two steps. It's not a fixed step. Basically, what does the product rule tell you? The first
times the second.
Yeah, the derivative of the second plus the second times the derivative of the first. That's why it doesn't matter which one you do first, because it's a plus in between. So which way you want to go? First times the derivative of the second? You okay with that? Well, the first function there is minus x. And then we're going to multiply that, the derivative of the second function. Well, guess what? We just did that. This whole thing is a derivative of the second function, right? Yay or nay? Derivative of the second function is exactly that derivative. So that would be times a minus x e to the minus x squared over 2. Okay? There's the first times the derivative of the second, and then it's plus the second. The second is this one, right? That's e to the minus x squared over 2 times the derivative of the first. What's the derivative of minus x? Anybody? Derivative of minus x. Minus 1, isn't it? So that just loses the plus sign there. You're multiplying by minus 1. Okay. Now, I'm going to rewrite that slightly. F double prime of x. Now, both of those terms, what Andy was saying before is a good answer now, has a factor. Wait. Before, let me just combine that. Okay. That's going to be a minus times minus is plus x squared e to the minus x squared over 2 minus e to the minus x squared over 2. Is that okay? Y'all agree with that? This minus times that minus gives you a plus. Okay? Those are multiplied together. This is subtracted, so don't get that one involved. Okay? And that would be a positive x squared e to the minus x squared minus n e to the minus x squared. Okay? Now this is where I was going to say Andy's idea is a good one here. Both of these terms have a e to the minus x squared in them. E to the minus x squared over 2. Now I just want to pause here a moment. He chose a very challenging problem to be the very first one you do with this. I think he could have started a little bit easier, but this is okay. We can handle it. If you factor out the e to the minus x squared from both terms, what do you have left? In the first term, x squared. And in the second term, minus 1. Perfect. So there you have got the second derivative. You started factoring it. We can do one more, can't we? We can factor it one more step, can't we? E to the minus x squared over 2 times will x squared minus 1 factor? Somebody. Say again? X squared minus 1, will it factor? I think I'm going to be sending some people back to Math 100. Maybe
X plus 1 times x minus 1.
X plus 1 times x minus 1. I was just kidding. Okay. All right, we factored that completely. Okay? Now, that's taken us so long we may have forgotten our steps. Let's go back and see. To apply that theorem, here's the theorem. What we do, locate the values for which either the f double prime is 0 or f double prime does not exist. So let's go back. We found f double prime. Where is this equal to 0? Any place? What would have to be true for that to equal 0? By the way, it's a product of 3 different factors. So what would be required for that to be equal to 0? Again, this goes back to Math 100, huh?
Any of those factors can be 0?
Yes, if any of those are 0. So either e to the minus x squared over 2 has to equal 0, or x plus 1 has to equal 0, or x minus 1 has to equal 0. Okay, now this may be a challenging question for you, but hopefully not. Where is e to the minus x squared over 2 equal to 0? Anybody? here's a little hint. Here's what one of these forms is what e to the anything is going to look like. It's going to either look like this or it's going to look like that. Guess what? It never, ever, ever equals 0. Now, if you put a minus sign in front of it, it would look like this or this. Again, never equal 0. So the exponential function will never be 0. Now, you can manipulate it and have a e to the minus x squared plus 1 or something like that. Or no, actually minus 1, and then it probably would be 0 somewhere. But it wouldn't be because it's an exponential function. That's a sum of the exponential function and something else. So an exponential function by itself will never, ever be 0. I'm trying to get my eraser. I kept clicking on my pen. Okay, there. Get this scratch out of the way. Okay. Now I can't get the pen to come back. Come on back, pen. Okay, there we go. So this one is never equal to 0. What do we have left? Either
x plus 1 or x minus 1.
Okay, x equal -1 or x equal 1. Perfect. Those are the two places where your first derivative is equal to 0. Okay? What's the other thing we have concern with? I said first derivative, second derivative. Where the second derivative doesn't exist. Is there any place on the real number line where the exponential function doesn't exist? No. I just showed the graph. It exists everywhere. Okay? And this linear function exists everywhere. That linear function exists everywhere. Though there is no place where it doesn't exist. So these are the 2 points that we have to deal with. Okay? Now, these form then your intervals. You need to pick some number to the left of -1. That could be what? I'm going to call it, okay, -2. Something in between -1 and 1. Real easy number. 0. And something to the right of 1. 2. Why not? So those are our test values. Okay, that's what it said. Use those to determine your test intervals. We just did. We took some test values. And now we look to see what the sign of the second derivative is on each of those places. So let's do f double prime of -2. Okay? I kind of like using the factored form, perhaps. This will be e to the minus, what's -2 squared? What is -2? That's a plus 4 over 2. So this is going to be e to the -2, isn't it? Does everybody agree with that? Okay. This would be -2 plus 1 would be -1, and -2 minus 1 would be -3. Okay? And I'll just tell you right now, I think you can do the math here. What's the product of those three numbers? Don't give me an actual number. You can leave an e in it. What do these two multiply to be? 3e to the -2. Okay? Now, all we're interested in here is the sign of the second derivative in that test interval. So what's the sign of the SIGN sign of that second derivative there? Positive, because e is always positive. So you got a positive 3 times a positive number, so it's positive there. So what does that tell you? Anywhere to the left of -1, what is that function doing? If it's positive second derivative, that means it's concave up. Okay. Now, I don't know the shape it's taking, but it's concave up in that interval. Okay. Now, what is it at 0? Let's do f double prime at 0. And again, that would be e to the 0 times 1 times, help me somebody, -1. No, up here. Put in a 0 for your x. See, I put a 0 in here, and that gave me e to the 0. 0 squared is 0. Divided by 2 is still 0. E to the -0 is still 0. Okay, so, and then this would be a 0 plus 1 is 1, and 0 minus 1 is -1. What's the sign of that? What is the value of e to the 0? No, e to the, the whole thing is -1. You're right. E to the 0 is 1. 1 is 1, but -1 is -1. So one negative number out of 3 factors, that's going to be negative. 1 times 1 times 1 is 1. So what does that tell you about the second derivative? What does that tell you about the function there? Second derivative is negative. Concave downward there. So it's concave upward on this interval, concave downward on that interval. So let's go to positive 2. F double prime of positive 2 would be e to the minus, and again, positive 2 squared is 4 over 2 is 2, so e to the -2. And then what is 2 plus 1? 3. And what's 2 minus 1? 1. Okay, so what is this? I really don't care what the value is. I want to know the sign of it. Positive. It's a plus 3e to the -2. E to the anything is always positive. Okay, so that's a positive number. That means it's what? Concave up at 2 as well. So it's concave up to the left of -1. It's concave down in between -1 and 1, and it's concave up past x equal 1. That's all we were interested in this problem, so I'm going to erase my scratch. Well, let me just do it here. Concave up on the interval from -infinity to -1, and from 1 to positive infinity. Okay? It's concave down. I can't write. Okay? From -1 to 1. Okay. That summarizes what we just said. So, let me clear what I wrote. I'm sure y'all are saying, yes, please get that scratch off of here. Okay? Any questions before I clear it?
Give me a bit. Let me take a picture real quick.
Keep it a little bit longer? Is that what you said?
I just need the bottom part.
Oh. You want me to?
I got it.
You got it?
Yes, sir.
Anyone else need it a little longer? And my writing stinks. This is concave up. This is concave down. That's supposed to be a C. It looks more like a V. Okay. It's really ugly. All right to erase? Anyone still writing? Good. Okay. So determine the open intervals on which the graph is concave up or concave down. Begin by observing that f is continuous in the entire real number line. That's important. because the exponential function is continuous everywhere. It's also smooth everywhere, okay? So that means you can take a first derivative. So we did it. And it says, next find the second derivative of f. Well, first you have to take the first derivative. And that's exactly what we got, minus x e to the minus x squared over 2. That was using the chain rule. Take the derivative of the outer function is e to the minus x squared over 2 times the derivative of the inner function, which here was minus x. Okay. Then we take the second derivative. Okay, and the second derivative was the first times the derivative of the second, which is exactly repeating this derivative again, because that's what we were taking, plus the second times the derivative of the first, where the derivative of minus 1 is minus 1. So that gave us a positive, well, they skipped the step or two and then went straight to factoring it out, e to the minus x squared times at x squared minus 1. That is your second derivative. Okay. Now, we found the second derivative. Next step, set it equal to 0, because where f double prime is equal to 0, and that's going to be where x is equal to plus or minus 1, because the e to the minus x squared over 2 is never equal to 0. So they just sort of left that part out, but it's true. Okay? And f double prime is defined on the real number line, because this second derivative is defined everywhere. Exponentials defined everywhere. Polynomials are defined everywhere. So the product of them will be defined everywhere. You should test f double prime on the intervals between 0 and minus 1, minus 1 and 0, minus 1 and 1, and 1 and infinity. Okay? And it sort of tickles me. I don't know why the graphics people can't get the fonts to be the same. These are darker and bigger than those. I guess that infinity, they only have one size. I don't know. But anyway, that's what it is. Okay? So we're going to pick a test point in each one of those intervals. And they chose negative 2, 0, and 2, just like we did. They got the sign of the first derivative to be positive in that first interval from minus infinity to minus 1, to be negative anywhere between minus 1 and 1, and to be positive everywhere beyond that. Now, don't think that you can draw the graph just based on that information. To draw the graph, you have to go back to the function. Okay? So I'm going back to the function here. They didn't tell us the graphic, otherwise I would have. Wait a minute. I'm sorry. Going in the wrong direction here. Okay. Hit the wrong button, sorry. Here's our function. So we are needing to find f of x. We did f prime, or no, f double prime. We need to know what f of minus 1 is. Okay? And what would that be? Anybody? E to the what? I'll write down the e. Negative 1/2. Perfect. Okay? Now, that's something like 1 over the square root of 3. It's not exactly the square root of 3. It's 2.7 blah, 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 blah. It goes on forever. But I always approximate it the square root of 3. Okay, square root of 3 is something fairly close to 2. Not quite 2, but getting close to it. So this is something less than 1/2. Okay? How about f of 1? That's our other point where the second derivative was 0. What is that value? Anybody? E to the negative 1/2 also, because you square it in the x, and it doesn't matter whether it's plus or minus, it's the same. Okay? So, and that's also something a little bit Did I say less? I think it's a little bit greater. Let's see, did I say it right? Yeah, a little bit greater than 1/2, okay? So let's go back to our graph and see if that makes sense here. Here is 2, there is 1. Oh, we didn't do that point. Let's go back and just do where it's equal to 0. Let's just do that one because that's so easy to do. What is f of 0? Anybody? 1. Exactly. Okay. So we go back here to our graph. Here. There's 1 right there. 1/2 would be here, so this is a little bit greater than 1/2. We know the function never, ever becomes negative, so it's going to approach infinity here. Approach 0, going to positive infinity or negative infinity. It goes through here. It's concave up on this side because notice it's just barely curving upward here. It's definitely curving downward here and barely curving upward here. So doesn't take much of a curve, just any curving at all, and that's concave upward. Concave downward. Does that make sense? So you always have to go back. If you're going to plot the graph, you have to go back and plot points for the function. Okay? Now what we didn't do for that function, and let's go back and do it. Oh, I've already erased it, didn't I? Oh no, here it is. I erased mine, but they did theirs. F prime, what do we do about f prime? If we set that equal to 0, or where it doesn't exist, that may give us our critical points. So where is that one equal to 0? And again, that's the product of two entities, minus x and e to the minus x squared over 2. Is that 0 anywhere? Anybody? X equals 0, and that's the only place, because it's where that first one's equal to 0. X equals 0. Because this one's never, ever equal to 0. An exponential function by itself is never equal to 0. Okay? So where the first one is, where is minus x equals 0? When x equals 0. So there's your first derivative. That means you could have a maximum or minimum there. And here, when we know that it's 1 there, negative 1/2, e to the minus 1/2 here, e to the minus 1/2 there. Those are both a little bit greater than positive 1/2. Then guess what? No, I didn't say that. Yeah, well, something like that. You have, and you know it's concave down here. That has to be a maximum. These are sloping always away, but always concave up. You're not going to have any more critical points. Okay? Does that make sense? I jumped a little bit ahead there, but since they drew the graph, I think it's helpful to show how they got that graph to look that way. Okay. Any questions? All right, that's exactly the same thing we concluded. Concave upward in this interval, concave downward in that interval, and concave upward in this interval. Now notice again, they always say open interval. You don't have to put brackets on that. I don't care whether the plus or minus 1 is with either of those or the other. Just leave them, as an open interval. Okay. Note that the function in example 1 is similar to the general form of a normal probability function, probability density function, whose mean is 0. This is what that thing actually looks like. Are y'all at all familiar with a normal probability density function? Anybody? I'm guessing most of you are probably saying no, but you're saying that based on that big, long, complicated name and even a more complicated looking formula for that function. Okay? let me tell you what that is. That's your bell curve. And you've all dealt with that before, haven't you? Oh, did you, where were we? Are you going to curve the grades? You know, what you really are asking, but most of the time you're not, is you're going to put it under a bell curve. Now, what we have here, that sigma here, is what we call the standard deviation. That's the lowercase letter for the capital Greek letter of sigma, like that. This is sigma lowercase. Doesn't look at all like that. This bell-shaped curve is concave downward on the interval from minus your standard derivative to plus the standard derivative. So this right there tells you your minus 1 is your, or 1 is your standard derivative, standard deviation. This is minus sigma. I can't write a sigma. Okay, there it is. Okay. And anything beyond that, you're outside of that. So what you're asking the instructor to do, if you're going to grade on the curve, that means everything in here, those are going to be your, no, this isn't quite right. You need one more derivative out there. But let's just say it's at 2. That's saying these are your A's, these are your B's, these are your C's, these are your D's, and these are your F's. If you're grading on the curve, technically, the vast majority of your grades are going to be C's. A few B's and D's, and very few A's or F's. And I bet you most of you really don't want him grading on the curve, okay? You just want him to add a few points to everybody's score. That's not grading on the curve. This is grading on the curve, under the bell curve, okay? So be careful what you ask for. That bell-shaped curve is concave downward on that interval minus sigma to positive sigma, which we knew in our case was plus or minus 1. The function given in example 1 is continuous on the entire real number line. When there are x values at which the function is not continuous, the function not continuous, those values should be used along with the points where your second derivative equals 0 or your second derivative doesn't exist to form your test intervals. And I don't know what the S is doing there. I don't think it was supposed to be there. The graphics person just sort of threw an extra S in there. I don't know. Okay. I guess he started with a test interval and then he tried to put it plural and put the plural before and after the period. I don't know what he did. Okay. All right. Any questions so far besides typos? All right. Let's move on to, well, no, we're not going to move on to points of inflection yet because we've still got to do example 2. Any questions on example 1 before we leave it? Okay. Example 2. Determine the open intervals on which the graph of f of x is equal to x squared plus 1 over x squared minus 4 is concave upward or concave downward. Okay, I think they've introduced a new level of complexity here. Now, if I can read my writing, that is a 1. The pen is sort of dragging a little bit. Okay. What have they done with this 1? It basically was based on that statement they had at the end of the last slide. What else do you have to keep in mind here? In fact, I think it's a great practice. I'm not saying I always do it, but I think it's a great practice that anytime you see a function like this, you put a comma after it, and then you list any values that cause you problems. Do you see any values that cause you problems? Anybody? Help me, somebody. Bells and whistles should go off anytime you see what? There's about 3 special things we always look for. A few others if you're dealing with trig functions, but in just rational functions, what do we look for? What are things we don't want to ever happen? Because they can't happen. What can you never do? Divide by 0, and there's a division line. So anytime you see a division line and you have the variable underneath that division line, you have to ask yourself, are there any values for that x that would make that denominator 0? So I like to say it this way. X squared minus 4 cannot equal 0. The book usually does equal 0, and then those are the ones you exclude. I just say it cannot equal 0 to begin with. What would you do with that inequality to try to solve it? What's the F word?
Forward both sides.
Second?
Add 4 to both sides.
Okay, you could do that. That, if you're very careful, that will work for you every time. But if you're not very careful, you're going to miss one of your possible places you're looking for. What I recommend, what's the F word? Factor. Factor this on this side. Whenever you have a quadratic or larger degree, that's when I would try to factor. Sometimes you do want to add it to both sides. Every time you have a linear function, yeah, you get all your x's on one side and everything else on the other side. When you have quadratics, if you can factor, usually a good idea to do so. So how will this factor, or will it factor? Maybe it won't. Will that factor? Anybody? Help me. Anybody?
Yes.
How?
You go x and x.
X and x, got it.
Plus and minus.
Plus and minus, I love it.
And then you do 2 and 2.
2 and 2, okay. And what does that tell you? If the product of these two can't be 0, that means that either or both
X
plus 2 cannot equal 0. And not or, and x minus 2 cannot equal 0. It's not either or anymore. Neither one of those can be 0. So what does this give you?
minus 2.
X cannot equal negative 2, and x cannot equal positive 2. So I like to put x cannot equal plus or minus 2. That's just an easy way to write that. Okay. Identify that right off the top. Anytime, okay, that's the first case. You can't divide by 0. Tell me 2 other things you can't do. One has to do with taking square roots. What can you never take the square root of? A negative number, or any even root, okay, not just square roots. Cube roots, fine. Fifth roots, fine. Square roots and fourth roots and sixth roots, no, you never can. So the thing inside the radical, if it's got an index of 2, if you don't see an index, you assume it's a 2, an even index, but you assume it's a 2 if you don't see one, then the thing inside there has to be greater than or equal to 0. And what's the other thing you can never do? Another function. The inverse of the exponential function. What do we call that function? People who work in lumber work with these. Say again? Logarithm. Yeah, log functions, yes. Whether it's natural log, common log, any kind of log, you can't take the log of what? It's kind of a combination of the two. can't take the log of 0, and you can't take the log of a negative number. So for a logarithm, anything that's inside the parentheses of a logarithm has to be greater than 0. Not greater than or equal to, greater than 0. Positive number only. Here, all we're interested in is that denominator, x cannot equal plus or minus 2. Okay, so what's the next thing we're going to do? I'm going to erase this because this is just to find those values that can't be. Okay, and it's always a good idea to write those down so you don't start prancing down the primrose path and forget that you can't have values there. Okay, so what do you do from here? But the question is, determine the open intervals on which this graph is concave upward or concave downward. Even though it was a previous problem, you still do the same thing. You should get used to saying this now. Take a derivative. So let's do f prime of x. Now in this one, what kind of rule are you going to have to employ? Employ means to hire. No, use. Okay. What rule do you need here? Quotient rule, exactly. How does that one go? Help me, somebody. Low D high. Low is your denominator, so that's x squared minus 4. And what's D high is the derivative of the numerator. What's the derivative of your numerator? Anybody? Derivative of the numerator. Help me. 2x. 2x. Perfect. Oops, I left off my x. Okay, 2x. And what comes next? You got the low D high, right? Minus high D low. That's why it really makes a difference there. When you're doing the product rule, it doesn't make a difference which you take the derivative first and which you leave alone first. In the quotient rule, it really matters. That's why low D high always comes first, minus, and what's high D low? What's your high? X squared plus 1. And what's D low? Derivative of the denominator. Anybody? 2x. 2x. Perfect. Over what? Low, low, which is the denominator squared. X squared minus 4 squared. Now, if I were you, I wouldn't mess with that denominator. Just leave it like that from now on. Because you'll notice here, x still can't be plus or minus 2. It couldn't up here, it can't down here either. Okay? So just leave that alone for now. And let's fiddle with the numerator sum. Let's distribute the 2x up here and the 2x over here. What do you get? The first part. Help me, somebody.
2x to the third.
2x cubed minus 8x. Now, be careful here. Minus signs are only there to trip you up, so be very careful. What do you get next? Anybody? 2x cubed again, and then that's this minus times those two pluses, and this minus times those two pluses will still be a minus what? Another 2x. Okay? All right. And this is over this thing, x squared minus 4 squared. Okay? Now, simplify that numerator. Those two, fortunately, add to 0, don't they? What do the other two do? Help me. Negative 10x over x squared minus 4 squared. All right, that was the first derivative. If you're looking for concavity, upward or downward, what's the next thing you've got to do? You what?
I didn't catch the question.
To do the concavity, what do you have to do? First derivative is just a necessary step to get to what? What are you really interested in?
Second derivative.
The second derivative. So we're going to have to take the second derivative of that. Still, we're concerned x can't be plus or minus 2. It couldn't at the beginning. It still can't. It won't ever. So just ignore that part. And, oh man, what do we have here? There again is what kind of rule? Anybody?
Quotient rule.
Quotient rule again. How does that go? Oh, it's at least 5 minutes ago. Easy to forget. Low, which is x squared minus 4 squared this time, d high. And what's d high? Pretty easy. Help me, somebody. You want me to do all the work, don't you? What is it? Huh? Negative 10. Okay. What's the next part? Minus high, negative 10x, d low. Now that's the part that really stinks, okay? What are we going to have to do there? It is both a power rule and a chain rule. The power rule, you say 2 times x squared minus 4 to the first power. Then the chain rule part is derivative of the inner part, which is a 2x. Okay? I don't have my watch or calculator or anything up here. Oh yeah, I can see the thing. We still have a good amount of time because we started right at the right time. So we still have about 17 minutes, I think. Is that right? Or y'all are just, okay, never mind. Okay, over low, which is x squared minus 4 to the 4th power, because you square that denominator again. So again, we're going to clean up the numerators. Let's distribute first, and what do we have? Minus 10 times x squared is minus 10x squared. Minus 10 times a minus, wait. Sorry. You can't do that because that thing's squared. Okay. I knew this was going to get ugly really, really fast here. What we have to do is square that first term. Okay? That's going to be square the first term, x to the 4th, twice the product of the two terms, minus 8x squared, plus the square of the last term, plus 16. That's what we multiply by the negative 10, minus, and this one we can just go on and write down, I think. Okay, a minus times a minus is a plus, okay? And we've got a 10, a 2, and another 2. That's going to be 40. You have an x and an x and an x squared. That's going to be x to the fourth. I love this problem, don't you? Okay, so that's the first part. Then you've got a 10x times 2x, that's 20x squared. Well, you got that same 40. 40 times a minus 4. That's a 40x squared times minus 4 is minus. Okay. I'm sorry. That first one was a plus. I'll put minus. I forgot to go on and change it. But the second one's going to be a minus. Okay. And why is that? Because the minus here that you changed to a plus, now it's going to change back to a minus of that. So that was going to be a 40x squared, 40x squared times a minus 4 is minus 160x squared. Okay. Whew. There's your numerator. Over x squared minus 4 to the fourth power up here, down here. All right. Now, if you distribute now here, you get a minus 10 times this. That's a minus 10x to the fourth minus 80x squared. That's the 10 times, plus 80x squared, sorry. Plus 80x squared minus 160. Okay? And then you got a 40x to the fourth and a minus 160x squared. Running out of room rapidly over that denominator. So let's combine like terms. Looks like a 30x to the fourth. I'll write it up here. 30x to the fourth. That's these two. Minus 80x squared. Minus 160. Okay. All that's over that denominator. Okay. Whew. Goodness gracious. Now, what we're interested in, there's your second derivative. What we're interested in is what? Two possibilities. Where the second derivative is 0 or where it doesn't exist. All right. Now I'll tell you where it doesn't exist. Same place the whole function didn't exist, plus or minus 2. Okay? That is carried through. It's just gone up in power every time you took a derivative. But it's still plus or minus 2. So those are going to be two places of interest because the function doesn't even exist there. The first derivative doesn't exist there. But we got to consider that as a boundary of an interval. So what we're really interested in is where that numerator, that's going to exist everywhere, so where that's equal to 0. So I'm going to try to simplify things a little bit by dividing everything in that by 10 and making it a 3x to the fourth minus 8x squared minus 116. Because I set it equal to 0, then divided by 10. I just didn't want to write all that down. Now the question we have is that equal to 0 anywhere? What would be your approach to it? What's the F word? Now, before I get too carried away here, I want to make sure. I think I've done something wrong. Let's go back down here to that second derivative line we got. We got x minus 4, x squared minus 4 squared times a minus 10 minus a minus 10x times 2 times x squared minus 4 times 2x. Now they came up with a different answer than I did. So I got to doing things too quickly. Let's see. You see, they skip so many steps that it's hard to follow. Okay, let's go back. I'm going to go up here and erase. Well, I'll wait and erase later. Or maybe I'll put here. Okay. All right. Let's see what we got. X squared minus 4 squared is x to the fourth minus 8x squared plus 16 times minus 10. Got it. Over here, I wiped out the minus and the minus here, so that's a plus, and we had 2 times 10, that's 40x squared, or x to the fourth there, using that first term, minus 40 times that is 160 x squared. All right, where did I botch something up here? They lost the entire x fourth term, and I still have it, because I have a minus Oh, I know what they've done. We didn't do anything wrong, I don't think. Okay, we were starting in the right path here. Let's continue. They just skipped way too many steps. Okay, I see what happens now. Okay, let's see if we can factor this. Okay, we're running out of time. The only possible factorization for this is 3x squared and an x squared. Agreed? And then you got a minus at the end. So I'm going to guess this is going to be a minus here and a plus here. I'm cheating, okay, and here's why. Because I want very badly to have a factor of x squared minus 4. So let's put a 4 here, and that would make this have to be a plus 4. Let's see if that works. 3x squared times x squared is 3x to the fourth. That works. Fine. Okay. 3x squared times minus 4 is minus 12x squared, and this is going to be a plus 4x squared. That gives us minus 8x squared, and that gives us minus 16. That works. Okay? So, we were doing right before. I'm glad I didn't erase. I started to, but I didn't. This factors as 3x squared plus 4 times, I'm having trouble with my boxes here. There we go. 3x squared minus plus 4 times x squared minus 4. That's what the numerator factored as, divided by the x squared minus 4 to the fourth power. So this one cancels one of those out, and that gives us a, I couldn't get rid of the 10. I thought I could, but I can't. Okay, that's still a factor. That 10 is still in front. Okay, so this gives us 10 times x, 3x squared, that's the square there, plus 4 over x squared minus 4 cubed. Okay. Now, what we want to do is set that equal to 0, and that's where I'll lose the 10. I want to put it back in just so you see the same thing that we had before. Okay. Is that ever going to be 0? And the answer is no. Wait, yeah. Because that numerator, 10 is not 0, and this one, see, I was right to throw away the 10. This thing can never be 0 because it's positive. X squared is always positive. 3x squared is always going to be positive. 3x squared plus 4 is always going to be positive. Well, 3x squared could be 0, but you add 4 to it, it's never going to be negative. Okay? There are no points for which the second derivative is equal to 0. That's what our conclusion is. So the only points we have to consider are where the function doesn't exist anyway. So we pick a value to the left of that, like minus 3. Pick a value in the middle, like 0. And pick a value to the right, like plus 3. And we'll evaluate our second derivative there. Okay? Now that's going to be a little rough to do. I don't have enough room to do it. So f double prime at (10) times 3x squared plus 4 over x squared minus 4 cubed. Okay, I'm sorry. I'm writing it in the wrong place. I need to do a lot of erasing because I just don't have enough room to write. Let me erase up here. Okay. Okay. I think I erased too much, but it's okay. F double prime at, I'm in a hurry and I'm making so many stupid mistakes. Okay, mostly in writing. F double prime at -3 is going to be 10 times 3, and -3 squared is 9 plus 4, okay, over 3 squared is 9 minus 4, okay, and that's going to be all you're interested in is whether it's positive or negative. And guess what? That's positive, right? That's 10's a positive number, 3's a positive number, 13's a positive number, 5's a positive number. So this is positive. That's all you're interested in. F double prime at 0, that's going to be a lot easier to evaluate. That's going to be 10 times 4 over -4 cubed. And again, I'm not really interested in its value. I want to know what its sign is. And that's going to be negative. Because your numerator is positive, your denominator is negative. Because -4 cubed is -64. And then the f double prime at 3, that's the third value out here. That's going to be just like the other one was. That's going to be 10 times, and 3 squared is 9. Actually wrote that wrong. Yeah, that's 27 plus 4. That's going to be positive. 27 plus 4 is 31 over 5 cubed. Doesn't matter what it is. You know, it's going to be left off my cubed up here too. Okay, it doesn't really matter what the value is. What matters is it's negative. Okay, because your denominator is negative. So what does that tell you? That all they're interested in. Determine the open intervals on which the graph was, I'm sorry, this one's positive. Okay, because that's positive. It's concave up from -infinity to -2. Okay, it's down from -2 to 2, you better put parentheses there because it's not even defined that either one of those function isn't, much less the second derivative. And it's positive up again from 2 to infinity. What a problem. And that's what they got to. Concave up from negative infinity to negative 2. Concave down from negative 2 to 2. And concave up again from 2 to positive infinity. Now, they do show what that one looks like, and we are out of time. Basically in the book, concave up over here, there's your vertical asymptote at -2, horizontal asymptote here, x-axis here, comes up and does something like that, and then at 2, yuck. Okay, at 2, it's concave up again. Concave up, concave down, concave up. That's a discontinuous function, discontinuous first derivative, discontinuous second derivative, but those points of discontinuity, your vertical asymptotes, that's what you use as your test point. There was no place you had in a point of inflection, which we haven't named it yet, but that's where the second derivative is 0. All right, sorry we ran out of time. We'll start next time with points of inflection, which I just used the term out of turn. I think you do have enough covered that you can do homework exercises, any of the odds 3 through 13. They're all at Calc Chat. 11's at Calc View. Number 13, by the way, has a trig function in it, which they already limited you to places where that's defined. Okay? And stop right there. So just 3 through 13, odds 3 through 13, all at Calc Chat. 11's at Calc View. Any questions? Sorry we ran out of time. Anybody? All right. If not, I'm going to stop the sharing. If no questions, I can't hear any. Stop the sharing, and we'll end our meeting, and I'll see you on Wednesday, okay? Still got Jonah, JJ, Joanne, Houston, and Andy. I think that. I didn't want to interrupt you at the time, but for a period of time, Jemanuel and Kyle both logged in and then disappeared again. Okay, Jemanuel did. That's good. And who else? Kyle. Okay. Yeah, Kyle has to go to the other campus. What? No. Okay, never mind. Okay. Remember, he always did in class. Okay. Good deal. Thanks for telling me. Okay. I told y'all to speak up if you came in, but you were already here. Okay. They didn't know to. All right. I'm going to end it now. We'll see you on Wednesday. Bye-bye.